In question number 6, from a uniform solid sphere of mass m and radius r, a cavity of radius r by 2 has been formed, touching the internal surface of the sphere as shown in the figure. Then we have to check the validity of given options. In option A, we have to find out the gravitational field at point A. So if total mass is m, then the mass of this cavity would be m by 8, and the center of this cavity is at a distance of 3r by 2 from point A. So for the complete sphere, this point A is the surface point. So we can write the gravitational field at point A as gm by r square, and for this cavity part we can write the gravitational field at point A as minus g into m by 8 divided by 3r by 2 whole square, and the direction is along positive x-axis, that is I cap. So if I solve this, the value comes out to be 17 gm by 18 r square into I cap. So option A is correct and B is wrong. Now the direction of the gravitational field at this point is in this direction, and we can see that the direction of the gravitational field inside the cavity is in this direction, and we know that in the direction of gravitational field potential decreases. So first potential decreases and then it increases. So there is a point where the potential is minimum, and at this point the electric field is 0, as we know that the relationship between E is equal to dV by dr. So at the point where the potential function is minimum, the electric field is 0. So option C is correct because the potential first decreases and then increases, and option D is also correct. So the correct answer for question number 6 are option A, C and D. Let's move to question number 7. In question number 7, the spring of a spring constant K is unstretched when the slider of mass m is at position B. So this is the natural position of a spring. The arrangement is in vertical plane and the friction is absent. The slider is released from position A. Then we have to check the speed of slider at position B and the normal reaction by track on slider at position B. So it is given that this is the normal position. So the spring is in elongated position. So at the moment when the slider reaches to position B, let it have velocity v, and this reference frame I am considering as 0 gravitational potential energy reference frame. So the loss in potential energy is equal to gain in kinetic energy. So I can write half k into x. So elongation is, this is 3r by 4, then this is 5r by 4. So 5r by 4 minus r square plus mg, if m is the mass of the slider, into its heights from the frame, that is 3r by 4 is equal to half into m into v square. So if I solve this, the value of v comes out to be 5 by 4 under root of gr. So option A is correct and B is wrong. Now at the moment when the slider reaches to position B, the normal reaction experienced by the slider due to track is in this direction. So N is equal to m into v square by r, as the spring is in natural length and friction is absent. So if I substitute the value of v square, then it comes out to be 25 by 16 mg. So option C is correct. So the correct answers for question number 7 are option A and C. Let's move to question number 8. In question number 8, a uniform rod of length 12 meter is held on a horizontal table with length 9 meter is projecting horizontally over the edge. The rod is released from rest and it starts to slip when it has turned through an angle theta is equal to 30 degree. Based on given information, we have to choose the correct options. So we have to find out the limiting friction between rod and table before slipping and the angular velocity of the rod at time of slippage. So let's analyze the situation. Suppose this is a table or edge and this is the rod whose length is L. So this length is L by 4. Now the rod is rotated by an angle of theta is equal to 30 degree. So let the position of the rod is something like this, and it is rotated by theta, that is 30 degree. So the position of the center of mass at this moment is somewhere here. This is center of mass, and if the rod is rotating with angular velocity omega in this direction, then we can write the equation of torque about the point of contact. So mg is acting in this direction. Let m is the mass of the rod. So m into g, gravitational force, will act in this direction. So first of all, I have to find out what is the angular velocity at the instant of slippage. So in order to do this, I am considering this as my zero gravitational potential energy reference frame. So the loss in potential energy is equal to gain in kinetic energy. So I can write mg into this separation would be L by 4 sine theta or sine 30 degree. So L by 4 sine 30 degree, that is half, is equal to half into I about this point of the rod. So ml square by 12 plus m into L square by 16. I have applied a parallel axis theorem into omega square. On solving, the value of omega comes out to be under root of 12g by 7l. So option C is correct and D is wrong. Now at this instant I have to find out what is the value of the limiting friction. So the limiting friction at this moment is acting in this direction, Fl, and the component of mg in this direction is mg sine 30 degree. So about this point, the center of mass is moving in a circular path. So we can write Fl minus mg sine 30 degree is equal to m into omega square into r. So this r is L by 4. So if I solve this, the value of limiting friction comes out to be 13 by 14 mg. So option A is also correct. So the correct answer for question number 8 are option A and C. Let's move to question number 9. In question number 9, in a fixed tube of uniform cross section and dimension as shown in figure, liquid of density rho is filled up to the level as shown. Level is maintained using a valve. Suddenly the valve is open. If A is the acceleration of liquid just after opening the valve and delta P is the pressure difference across the horizontal arm of the tube, then we have to find out the value of A and delta P. So the acceleration is equal to the extra force acting on the liquid, which is because of this liquid, divided by the total mass of the liquid. So when the valve is open, the acceleration A can be written as the extra force due to this liquid is m into g. So m can be written as density, that is rho, into length. So this length is L by 2 into, let the cross sectional area is A. So this is the mass into g divided by total mass. So total mass would be rho into 7L by 2 into A. So this comes out to be g by 7. So option A is correct and B is wrong. Now the pressure difference between the two ends of this horizontal arm can be written as delta P is equal to mass into acceleration. Mass of this segment into acceleration. So mass of this segment is rho into 2L into A into acceleration, that is g by 7 divided by cross sectional area A in order to get the pressure difference. So this comes out to be 2 rho GL by 7. So option D is also correct. So the correct answer for question number 9 are option A and D. Let's move to question number 10. In question number 10, the fundamental frequency of a wire of length L kept under tension T is F0. The wire is then supported at distance x, where x is very less than L, from the middle of the wire as shown. And the wire is again set into vibration in fundamental mode in both sides. If F1 is the fundamental frequency of left portion and F2 is the fundamental frequency of right portion, then we have to find out the value of F1 and F2. So we know that when the wire is stretched at both the ends, then the fundamental frequency F0 is given by 1 by 2L under root of T by mu. Now when the tension is kept same and the wire is then supported at a distance x from the midpoint, then in that situation let the frequency in this is f1, which is given. So f1 can be written as 1 divided by 2 into L by 2 plus x into under root of T by mu. So this can be further written as 1 divided by L plus 2x into under root of T by mu. So if I take L common, then this can be written as 1 divided by L into 1 plus 2x by L into under root of T by mu. And further it can be written as, if I multiply this by 2 and numerator also by 2, then this after binomial expansion we can write in this way: 2 into 1 minus 2x by L into f naught. So on further rearranging, I can write 2f naught into 1 minus 2x by L. Similarly, for f2, I can write 2f naught into 1 plus 2x by L. So option A and B are correct. If I find out the value of f1 minus f2 modulus, then it is 8 times f naught x by L. So option D is wrong. So the correct answer for question number 10 are option A and B. Let's move to question number